Okay, how about that? Okay, so that was an artifact of Wimba kicking me off, and I didn't realize that had kicked off the audio. Okay, so come on, minimize. Maybe not. There. It's gone. Okay. So we've got, in answer to your question, there's one text section output in the output file. There's one data section in the output file, one BSS section in the output file. You can configure your linker to have two different kinds of text sections, but you'd have to name them differently. Okay? And there's nothing magic about .text. That's just a convention that we apply. When we tell the linker, I want you to create a text section, I want you to take the text sections from the input files and make it into the text section of the output file. And we're going to see the file that we use to tell the linker to do that. Okay?
One more question.
Go ahead.
So once you're inside the text section, are you going to be able to tell what's part of the FIFO, which part of the FIFO name? Are they clearly put in that order, or are they kind of put in there?
Okay, so the question is, once you've built the text section of the output file, is it easy to distinguish between the components of that text section that came from FIFO and the component that came from FIFO main? From the perspective of an executable file, you don't care. You typically don't need to distinguish which section came from what input file. There is a script that we will be showing that says when you create your output section, include the input sections in this order. So you can tell the linker, I want you to link it in this order. But for the most part, you don't need to distinguish between it, and I don't know why you would want to, but I don't think there is placeholders put into there. There are ways you can go about doing it, but you'd have to tell the linker to add some information saying, as soon as you're done with this input file's input section, put a place marker there. Okay. So you assemble your text sections into an output file text section. Note right here we have printf text, and what printf text means is we also include the text sections of any libraries that we're going to import and include. Okay. We also have the data sections from our input files, and we compile those into the data section of the output file. So the linker's job is to glue the input sections into output sections. Yep.
How is it then, so we have a main and then a FIFO separate them, but how does that even work if they're all being put together, and how do they even not know what's going on if they're linking together?
Okay, so the question is, it's kind of confusing how we have a main and we have stuff all scattered in different files. How does it all work together?
Yeah, well, kind of, like the whole point of doing the main, at least what I understood was you told me, so that FIFO doesn't know what main's doing, main doesn't know what FIFO's doing, but then you're sticking them all in the same file and they're being linked together.
Okay, so we're trying to correlate this idea of having walls and abstractions, where I told you don't want to have FIFO knowing what FIFO main's doing. Okay? That's not for the executable. You don't want to have the executable have them separated. You want to keep programmer from shooting programmer in the foot. Those are abstractions for humans. Okay? We want to undo those walls and those separations at the time we build the program, because all these artifacts of the program need to work together. Okay? So, very good question. You want to have your program structured so that when a human goes through and tries to read and understand and modify things, that it's easier for the human to be able to comprehend what the program is doing. And all that structuring is how you think about your program and the structures that your high-level source code uses to specify your program. But you want to compile all that stuff out by the time you get down to here. You want all of it to be one big kludge of a mess, because that's how programs have to work when they run. Okay? Good questions. Other questions? Yeah, Jonathan.
Does order matter for the linkers? So, I mean, like if you specify the specific order, say, you know what the path or general path of your program is, can you order your object files in such a way to kind of link those together so it takes that, and then anything else that is an unlikely path you take will be placed elsewhere?
So the question is, does order matter, and can you specify search paths for object files in a way that it'll look in the right spot first and not travel down directories it shouldn't go in?
Or, I mean, if you have like a branch of an if statement that you take all the time, and so you want that to be close to all the code where it's going to be executed.
Okay.
Then the other branch you hardly would ever take. Can you specify to place that?
Okay.
From it where
So the issue, and I'm going to try to repeat it again so it gets on the recording, but the issue is if you have an if statement and you've got two legs of the if statement and you know with high likelihood you're going to take the if and not the else, can you provide a hint to the linker or to the build tools to optimize for that common case to where you put the stuff you're going to jump to close by? Now the question then becomes, how would proximity impact correctness or performance? So under the assumption that the proximity in the code did impact performance, and there are ways that it does, and you have to fiddle with instruction caches in order to justify that proximity does impact things. That would be an issue, figuring out proximity and all that. You'd have to get pretty specific with the layers of the onion, peeling things back to customize what goes where, and the tools don't natively support that. So they don't really look at, you have to some degree some support within the compiler for understanding or trying to predict the frequency of a branch being taken. And it does apply that knowledge when it's, for example, compiling a loop. Because when you have a loop, you're more likely going to jump up back to the top of the loop than you will to jump out of the loop. Okay? So knowledge like that is applied at compile time. But once the code that you're talking about, the leg of the if as opposed to the leg of the else, once those two guys are in separate object files, the compiler can't control that anymore because the compiler only looks at one source file at a time. So rearranging the code that goes over to here, and if you can kind of shove that over to here so it's close in proximity to this guy, usually the granularity that the linker works on is section by section and file by file. So if you would have to specify when you compiled your file that has the if leg to partition the code that goes into the if into a special subsection, and you configure your linker to say, pick this subsection and put it next to this guy over here. Anyway, it'd take an awful lot of customization. You'd be better off just moving the source code over to one file and calling it good from there. Other questions? No other questions that'll take me at least 10 minutes to answer? Okay. So, how do you tell the linker what to go and do with itself? We have two files here in the build chain that are important. One file, you tell the linker what to do. Another file, the linker tells you what it did. What you tell the linker how to do what it does is the armelf.x file. The linker tells you what it did with the map file. Okay? So armelf.x file, this is what you call a linkage editor script, okay, or configuration script for the linker. Different types of linkers have different types of scripts like this. This is typical for the GNU tool chain, okay? Every time you use GCC on the host or the target, or any time you've used GCC, it references one of these. Not necessarily ARMELF, because that's for our particular target. But GCC has, under the hood, built into it, one of these script files. Okay? We don't usually need to deal with it because we can ignore it and life goes on. Because the default settings that it has usually apply to all the programs that we're trying to build. When we're trying to invoke a cross-compiler for an embedded system and we want to have another level of customization that we want to impose on our embedded program that we're building, we need to understand what this linkage editor script is and what it does and how it impacts things. Okay? There's a lot of stuff here. I'm not going to hold you to all of the stuff that's in here, but I do want to point out a few things so that you can understand kind of what's going on, because this really tells the linker what to do. And so you can kind of see why the linker does what it does. The reason for it is because we tell it to do it. Okay? All right, so these guys all in caps are kind of like macros. This is not specified in C or C++. This is in its own particular syntax, but it uses concepts like a macro. So these like output arch ARM. This is telling the linker, I want you to use the ARM architecture as your the architecture we're going to link to. Entry underscore start. This says, what is the name of the symbol where the program is going to begin execution? Okay? Burn that into your head. Remember that one. That's important. Okay? Start is the symbol name of the entry point of the program. Search dir. This is where you're telling it, this is like your include path, except for you're going to tell it where do you want to look for object files, where do you want to look for libraries. This is one path where it can look for libraries. That happens to be a path that was on my machine that I used to build the cross compiler. So it's going to look in Fall 2007 TS Tools install armelf/lib. It usually can find the libraries that it's after because it has relative path names built into it as well. Okay. Sections right here. This right here identifies the various sections of the output file and how we will compose sections from the input files to build those output file sections. Okay. What you see on the left side here, these are identifying names of output file sections. You see a colon followed by a brace followed by stuff. The stuff that's on the right side inside the brace is what you use to compose the section in the output file. So for the .interp section in the output file, I'm going to include this star means any input file. .interp in parentheses means the .interp section of each of those input files. This star is like a wildcard in regular expressions, or like when you're doing ls star dot something else. So any input file that I have, take the interp section from it, compose the output files interp section from all the interp sections of all of my input files. Okay, so that kind of makes sense? That's generally what the syntax is doing. This statement above it where we're saying dot equals 0x0021900. Okay. You can see a lot of dots in all of this. Dot hash, dot dinesim, dot interp. When you have a dot by itself, what that means is that's how the linker refers to whatever the current address that I'm linking to is. So when the linker links stuff, it says I'm going to start at a particular address and I'm going to start filling stuff up from that address. And wherever I put a particular instruction, that will end up being its address at runtime. Okay? So this is how I tell the linker, I want you to start linking the first thing you link at using this address. So I say dot equals 0x0021900. That says start linking based on the address of 219000. Okay? Yes?
So that's where the program was loaded in memory?
This script doesn't say anything. So the question is that will be where it gets loaded in memory. This script doesn't say anything about loading. All it says is assume the first memory location of the first memory location where you're going to be at when you execute the program will be 219000.
So that number, that's something specific to ARM.
Could be.
Not specifically.
Could be. Is it specific to the ARM processor? I'd venture. Well, that address had better reside in the region of memory that the ARM processor board that we have has available to it. Because all the addresses that are going to be in the program will be relative to this point. Okay? You won't have any addresses of any part of the program that will be before this point. So, for example, if you load the loader program at an address that is at the same location where you're going to load your program, you could potentially overwrite your loader with the loaded program, and that'll cause things to mess up a little bit at some point. Because if you overwrite your own program, you're going to end up overwriting the instruction you're supposed to execute next, and that'll cause your program that you're running to do something you don't want it to do. Okay? So there are reasons why 219000 was selected for our board. Is it a magical number on all ARM processors? No. How's that for a nice, clear, muddy answer? Okay. So dot equals 219000 means start linking at address 219000. So all this stuff about .interp through .reltext, this is all important because we're defining output sections in terms of input sections, but for the programs that we're building, none of these sections have anything in it. so we don't really care about it. We're going to scroll down until we get to the init section. Okay, the init section, right here what we're saying, we're going to define the init section of the output, and we're going to compose it from the .init section from any input file, okay? So now we say .plt, now .text. The PLT doesn't end up having anything in it. So the init section, this does have stuff in it in the programs we build. Now the .text section. What we're going to do is we're going to fill the .text section with any input files text section, any input files .text whatever else might have in there, .stub, GNU warning, GNU link, blah, 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 blah. Okay? So this is where we tell the linker, I want you to build the output text section from the input text sections. If you wanted to do the customization you were talking about, you would have had to hack a text here and maybe say, you know, the thing before the if statement's in a special type of section and the thing after the if statement's in a different kind, and you put in the output, the other if leg of the statement in the middle of there. Okay. .fini doesn't really matter. Okay, so right here in these provide statements. Okay. So we see provide underscore underscore etext, provide underscore etext, provide etext. These define variables. Okay? They initialize those variables. They define symbols. They initialize those symbols to a number. The number is dot. The dot refers to whatever the linker's current address that it's linking to when it gets to this point. Okay? So after it's stacked in all the init section and all the text section, the current location of where I'm going to link to next is going to be some number that's bigger than 219000. But I'm going to associate a variable underscore underscore etext with that number. Then underscore etext and then etext. These are three different variables, and they're all initialized to the current memory or the current location of where I'm linking when the linker gets to that point. Okay, another thing this script does, it'll say dot equals align 256 plus dot and 256 minus 1. What this does is it sets the current location of where I'm linking to an aligned address, an address that's aligned on a 256-byte boundary. Then I define the data section. The data section is composed of the input data sections, the input data dot whatever else sections, GNU link once. Okay. Alignment sometimes causes you to have spaces in your output file that don't contain anything. Because there are times where I need to make sure to skip over enough addresses so that the next address I start linking to is a multiple of some value. There are reasons for doing this, and we're not going to get into the reasons for doing it, but just there might be junk bytes in your executable just because you need to skip over in order to support alignment. Here's BSS, the better save space. Okay, we have this variable BSS start. We say BSS start equals dot. We also have this variable, which is underscore underscore BSS start underscore underscore. Note that these two guys are different. Why do we have two of them? I don't know. We do. Okay? So, but this tells you, if you ever wanted to figure out what is the beginning location, what's the beginning address of the BSS section, you can refer to one of these symbols. Okay? So the BSS section is composed of the .sbss section and the .bss section. So here we've got .bss. And that's composed of the input sections of .bss. All right. Yep.
So then both of those have two different BSS starts. They have two different addresses.
Yes. Okay, and then down here we have BSS end. So we say underscore BSS end underscore underscore, and then, you know, various permutations of underscores. All of that. Okay. But we basically what I'm trying to say is we define variables that mark the end of the BSS section.
All of these things are standard have to have.
So these are standard have to have symbols defined. Yes. So in order for the program to work correctly, you have to have that. Particularly the marking of the beginning and the ending of the BSS section are necessary. And in Lab 2, you'll tell me why. Okay, .stack. .stack, this is how we're going to define the location of where our stack is in memory. So the stack is a big chunk of RAM that we use for temporary memory locations, for holding things that we just need for a little bit of time. So we're going to say dot stack. We're going to associate that with the number 80000, and we're going to say underscore stack, which is a variable, equals dot. So that associates the underscore stack symbol with this number 80,000 in hex. And we're going to link to that location anything that's an input section dot stack. Okay, so this is how we tell the linker what to do. Now we're going to look at the map file, and this is what the linker tells us what it did. Yeah, Mitch.
How much of that is different than where the default is?
How much of it is different than what the default file is? Not much of it. A few numbers.
So what, in order to make it run on our board?
You don't need to change that file. I'm providing it, so in order to get this to run on your board, you don't need to change the rmelt.x file.
Right, but I'm just wondering if without it, it wouldn't work on our board then.
So without it, it would not work on your board, yes. And I don't make you answer the question. Well, between Lab 1 and Lab 2, I start to have you guys answer some questions that go towards the reason of why that won't work. As soon as we're done with Lab 2, I'll tell you about it, if you ask me. Can't give away the answers to Lab 2 yet.
We don't need to change, for example, that place curve or the new machine?
No. No. Won't hurt if you do. You don't need to change the search dir. Because this file gets automatically generated when you build the cross compiler. Because I built the cross compiler on my machine, it put that in there. But if you wanted to add some or change the location of the cross compiler or put it someplace else, because of the fact that the setup script that I give you guys, that sets up some paths, and that takes care of manipulating where that search dir is. Okay? Okay. All right, Mr. Linker, what did you do? So once we run the cross linker will output this big nasty file. Now what we want to do is go through this file a little bit to see what in the world did the linker go and do with itself. This map file starts with a bunch of file listings at the beginning. What do these guys mean? Well, this is the linker telling you, well, I had to link against the file libc.a, which was in this big location here. The reason why I had to link against libc.a is because I needed something out of the file exit.o, which is part of the archive libc.a. Any file that has a .a extension is kind of like a tarball or a zip file. It's not compressed, but it's an archive. It's a collection of object files. Okay, so printf is in there, exit's in there, all the other C runtime functions, and many more that you never want to learn about, but you're going to do it in Lab 2. They're all there in the .a file. Okay, so it'll mine the .a file to find a .o file that it needs. It needs a particular .o file because there's a symbol that it needs to link against, whether that symbol be a global variable or a global function. So this just tells you which files are the linker linking against as it goes through. So this line right here, this says I linked against blah, 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 CRT0.o because I needed the exit symbol. The exit symbol was defined in CRT0.o. Okay, so I had to link against impure.o and libc.a. I needed the impure pointer symbol out of exit.o, which is in libc.a, and so forth. Okay. We look down here. In particular, I needed to link against libc.a to get to printf.o because p.o references the symbol printf. Okay? So this is the linker saying, these are the files that I grabbed, and this is why. Okay. The linker gives you a little table of common symbols. It says these are some global variables, and I had to allocate them, and this is why. So it says there's a symbol called B that's 4 bytes long. It was defined in the file p.o. There's a symbol called erno that's 4 bytes long that was defined in this. This is just word wrapped around. Okay. That's defined in sberkr.o. So this is a summary file, and more information about B will be provided later on. Okay, so when in the linkage editor script, you can specify this is what memory looks like. The map file tells you, by the way, this is what I assumed memory looks like. What do we mean by memory? Well, we mean by how much RAM do I have and what address does it start at? So over here, this is the linker telling you, well, this is the memory configuration that I used. I assumed that I have RAM starting at address 0, and its length FFFF long. Technically, that's not entirely true for our TS7200 boards. We have 32 megabytes of RAM that is configured to begin at address 0, and it goes for 32 bits, however many Fs that is. Okay. There are slick things about memory management units on processors. You can actually program the memory management unit to say, well, RAM doesn't really begin at address 0, it begins at address FFFF. You can tweak things around like that. But our memory management unit is specified that the RAM chip shall be accessed in real mode, and it starts at address 0 and goes for 32 megabytes. So the reason why this is here is because let's suppose you had a processor that only had 1K of RAM in it. If you told your linkage editor script, I only have 1K of RAM and it starts at this memory location, if you started to link to addresses that were outside of that location or too big for that size, the linker will give you an error. It'll say, wait, you're building a program that's too big for your board. So it's just a seat belt that the linker puts in there. So if we defined a program that was bigger than 32 megabytes, potentially we could configure the linker to check for that. Okay, the next thing in the map file is a bunch of load commands. These load commands say, I'm going to link against crti.o, crtbegin.o, and crt0.o. So those guys are just files that I'm going to link against every time. So the linker says, I loaded these files. So I'm starting at address 219.0.0.0, and that's where I'm going to start linking. Now the linker comes through and it reports, I created a .interp section that had all of the interp sections from the input sections, from the input files. Likewise with hash, dynsim, dynster. These guys just list here and there's nothing in between them because there was no data in either there was no .interp section in an input file or the .interp section from each input file didn't have anything in it. So there was nothing to do. It just says, well, I tried doing all this, there was nothing to do. But now we get down to init. And I told you there was stuff in the init section, so the linker's saying, well, I got to the init, I'm creating an output section init, I started at this address, there's 0x20 bytes of data here, okay? So my directive was to include all of the init sections from all of my input files. So I'm creating the init section starting here, 0C, this is the input file that had an init section. crti.o had an init section, I'm linking it to 219.0.0.0. It was C bytes long, okay? So over here I have an init section in this file, crtbegin.o, that was 4 bytes long. And I'm going to start linking it at 219.0.0.c because I'm going to take all the stuff out of this crti.o file, the C bytes there, I'm going to start at 219.0.0.0, include C bytes of that. Then at 219.0.0.c, I'm going to include 4 bytes. 219.0.0.10, I'm going to include 4 bytes CRT begin. So I've got C bytes from CRTI, 4 bytes from CRT begin, CRT end has 4 bytes, and then I have the .init section from CRT in, which has C bytes that starts to get put at 219.0.1.4. Okay? So this is just how it's taking each of the individual init sections from any of the input files. These are the only files that had init sections that had anything in them. So I just included all those and started stacking them up, starting at the beginning link address that I had. Okay, the other thing to make note of is that the init section from crti.o at symbol 219.0.0.0 defines a symbol underscore init. So that's kind of like a global function. It's just a symbol, or it might be a global variable. But there's this symbol here that's defined at that address as part of the init section. Okay? So the linker tells you what input files it references, how many bytes it took from those input files for this particular section, and what symbols are defined there. Note that in these other sections, it just says there were 4 bytes, 4 bytes, 4 bytes, C bytes, but it doesn't have any symbols associated with it. So it begs the question, how do we access the data or the instructions that it put there? Well, that's a topic for a different discussion. Text section. Now here's where the bulk of what we're doing is. because we're writing a program and most of the program is actually instructions. So I'm creating the output section.text. I'm starting at wherever I left off with the init section. That's at address 219.0.20, and I've got 71E4 bytes to put in there. What are those bytes from? Well, I've got the text section starting at this address. I've got E0 bytes from crtbegin.o. Then the text section, 44 hex bytes from crt0.o. And crt0.o defines the symbols main CRT startup, underscore start, and start. And they are defined at these locations in your output file. Then I have the .text section at 219.144, 0x50 bytes from p.o, and here I have the symbol main defined at 219.144. Does that look familiar to anyone? That's why main prints out the number that it does. Okay? There, I gave you an answer to the lab. Okay, 219.194. At that address, I've got 78 bytes from exit.o that defines the symbol exit. Data section. Similar, we're compiling the data sections. At this point, I'm at 220574. I've got 718 hex bytes for the data section. I've got data that's defined in CRT_begin, the __DSO handle variable. Then I've got the data section from p.o that defines a single symbol called A. That A has the address 22057C. Should have seen that before too. Then I've got 2F0 bytes from impure.o, which defines impure pointer. Now we skip some stuff. We define the BSS section here. This is what the linker does with the BSS section. The thing of interest, after putting in a bunch of other shenanigans, you've got in here in common 220DA8, 4 bytes in p.o. This means I need to save 4 bytes when I instantiate or load this program to hold the symbol B. And the symbol B will have the address 220DA8. Okay, that's all there is to linking. Try to rattle off those hex numbers as fast as I did. That ain't easy. Okay, so any questions about linking and linkers and why linkers do what they do? So now what you should do is you should go back to p.c over here. And when you see p.c outputting the stuff that it outputs, you should be able to now tell me why main gets printed the way that it does, the address of A and the value of, well, I haven't told you about the value of B, I'm not going to. You should be able to tell me why most of those values get printed out the way that they do, and you're going to have to do a little bit of research to figure out the other one. All right, thank you. We're going to do theory lecture next time. We've been doing nuts and bolts the whole semester so far. We'll do theory stuff next time. We're going to lecture on chapter 2.
It's not bad. No, read you can use it when you want to close. Chemistry students, not bad.